All right, hello guys. First of all, can you hear me? I'm not sure if my mic's working today. Can you guys hear me? Give me a comment if you can hear me. Can you hear me? Yes, good. Okay, cool. Welcome to our first online lecture for you lot. So yeah, this is going to be how lectures are done from now on. So make sure you guys in future are, because you won't be in college next week. Thank you, Caleb. Can you guys, yeah, you can make sure you all got YouTube accounts so that you can put comments on the chat, and that's how I will go over stuff differently or check if anyone needs any help. Cool. So, seeing as we finished the syllabus, I thought let's revise the whole of mechanics because then we'll be really good at mechanics. And then after that, we'll start looking at pure and looking at some past papers via this setup as well. So, but let me guys know if you've got questions you want me to go through. Email them to me and I'll tag them onto the end of a lecture, or comment in the chat, which I'm following as well. I think there's about a 15-second lag today by the looks of it, so it's not too bad. So anything you comment, I should be able to get sorted. Cool. And tell me if I'm going too fast because it's quite easy to go fast on this. So I thought today we'd look at basically displacement, velocity, acceleration, first year stuff and second year stuff together to try and make as much sense as possible. So we're going to start off by talking about displacement. So, so displacement is a vector measure of distance. So if you were tracking something's journey, you could say if we start here, travel to the finish, and if that distance was 10 meters, and then if we traveled back the other way, another 10 meters, the distance you've traveled, well, you've gone 10 and then back 10, so you've traveled 20 meters in total. So that's your distance would be, or distance traveled, let's say. Distance traveled 20 meters. What would your displacement be? Write in the chat. I know there's a 6-second lag, but write what your displacement would be in the chat if you could. Well done, George. George got there first. He got 0. Well done. Your displacement is 0 meters because you are displaced no meters overall. You're back where you started. Good. All right. Equally, if we had a projectile being thrown from a 10-meter tall tower, let's just box this off so it's separate. If we had a projectile being thrown from a 10-meter tall tower, like that, what would the total vertical displacement be for the ball on the tower? So if you guys could again comment your answer. What is the total displacement for a projectile in that situation? Total vertical displacement. Oh, it's George Callum. Okay, I see. That makes perfect sense. Plus or minus 10. Yeah, total vertical displacement up there. Depending on which way you said was positive. If we say up's positive, our displacement would be minus 10. Minus 10 meters, assuming up is positive. Well done, Roddy there. So good. Well done, guys. Okay, one more of these little examples. If we had a projectile fired on a flat plane, what's our total vertical and total horizontal? So if you guys could tell me the vertical displacement, it doesn't come up very well. Vertical displacement and the horizontal displacement of this particle. Oh my god. This one. Can you tell me what the displacements are? So, George, is that George or Caleb? I'm really confused now. George is saying vertical is 0. Yep, because it starts and lands on the ground. So vertical is 0. Let's do that a bit better. Vertical dot dot 0. Don't forget unit 0 meters. And horizontal is going to be 10 meters. Assuming left is positive. Good. So that's a brief summary of your displacement. So always remember, displacement is a vector, so we need to consider it differently to how we consider distance. Cool, good. All right, so moving on. Let's talk about speed. And let's move that screen back down because we can't see what I'm writing. So speed. Speed is the rate of change of distance. And it's measured in meters per second to the power -1. In other words, it is how many meters, I never know. How many meters you travel per second. Or you could say it's how quickly your distance from the origin increases. Or decreases because speed is always positive. So let's measure this rate of change of displacement or distance in speed's case with time. And the difference between speed and velocity. Velocity is the vector form of speed. So hopefully this is all pretty obvious stuff at the moment. So let's talk about velocity. There we go. So velocity is the vector form of speed. E.g., it is the speed in a given direction, because vector quantities have size, which would be the speed, and a direction. So the way we do that, if we had, and we're talking back to kind of to projectiles here, if we had an initial speed u of 10 meters per second, we've got an angle with the horizontal of theta. Could you guys work out for me an expression for our vertical and horizontal speeds? So horizontal speed, let's call it ux. Vertical speed, let's call it uy. So quickly, could you guys come up with an expression for ux and uy? Not what I'm meaning to do here. 10 sine theta. So is that George or Caleb? I forget. Yeah, I mean, which is that? Is that vertical or horizontal? We need some clarity here. And we've got 10 cos theta. Yeah, those are the right answers, but which is which? Well, I haven't really said there. Sine is vertical, cos is the other one. The other one horizontal. Yeah, good. Okay, so ux equals u cos theta, and uy equals u sine theta. Cool, and you can remember that because of my little rule about cos being across, and I can actually demonstrate that really nicely if I get inside the angle. God, this is hard. So there's my speed. If I rotate across the angle, which you can literally see my hand is going across this angle, that's going to be cos. If I'm trying to find the other one, there, and we're joining by vertical. Vertical would be up here. This is really hard to do. There we go. Vertical, not going across the angle at all. Nothing in here. So across is cos is the way to remember these. And I guess we could put units in there as well. Both of these would be meters per second to the last one. Cool. All right, now let's talk about acceleration. Oh, no, what am I doing? Acceleration. Cool, acceleration then. So acceleration is a rate of change of velocity. Could be speed as well, rate of change of speed or velocity. Acceleration is meant to be a vector. Quite often we only deal with it in one direction anyway. So you can say rate of change of speed or velocity, and our units meters per second to the -2. So it's meters per second per second. Yeah, there's not much more to say about acceleration. It's how quickly your velocity changes or how quickly your speed changes. The acceleration due to gravity is 9.8. So g is an acceleration, little g, 9.8 meters per second squared, which is a common acceleration you're likely to use when anything's going up or down. Yeah, right. So let's talk about vectors, scalars, and our units, just to summarize everything so far. So we'll draw a little table, scalar, vector, units. So scalar, we got distance, we've got speed and acceleration. Vector, we've got displacement, which is probably not going to fit in this box. Displacement, yeah, just about. Speed, we got velocity. And the vector form of acceleration is just acceleration. Cool. Units, meters per second, and meters per second. Power -2. Cool. So quick summary there. Please let me know if I'm going too fast, but this is all revision, so hopefully you guys seen this all before. The idea here was just to get stuff straightened out in your heads. All right, so moving on from definitions, we're going to talk about when regions where we've got constant velocity. So in other words, our velocity is not changing and our acceleration is 0. So constant velocity, e.g. a is 0. Thanks, Caleb. All right, so when we've got constant velocity, SUVAT's not very useful. SUVAT's for constant acceleration. SUVAT assumes we have an acceleration. So for constant velocity, we use a set of different equations, and they kind of become a lot easier. So we got average speed equals distance over time, which you probably learned back in your GCSE. And you can kind of think about that. Speed is measured in meters per second. We've got meters. We've got time, seconds, meters divided by meters per second. So that all kind of makes sense. And if you rearrange it, you could get distance traveled equals speed or average speed times time. So you can get these simple equations, and that's what you would have used back in GCSE. You probably would have had this little triangle that they love in, in GCSE science. So you got speed, distance times time. So any of those, it won't be used very often in A-level maths, but sometimes it does crop up in questions, especially in the pure maths kind of stuff. All right. What else do we have for constant velocity? Actually, let's just erase everything here. Might be a nicer way of doing things. Cool. Right. Constant velocity. We also know displacement. So as we said just now, displacement is velocity times time. Same as distance, average distance or total distance is average velocity times time. Displacement is velocity times time. So we can add together different displacements. So our total displacement, we call it R, is equal to our initial displacement, we call it R0, which is where we were, plus VT. And if you look above, the equation says displacement is velocity times time, so VT is just how far we've moved. So this equation in words says where we are, or your total displacement, is your initial displacement plus velocity times time, which is the amount of displacement you've moved during this journey. So displacement moved. So we get to this equation, which again, the really important thing to remember about this is it only works for constant acceleration. And also this comes up quite often in vectors because all of these quantities underlined are vector quantities. So this will often be in the vectors part of a question. Cool. And we can kind of see this in terms of vectors as well. So if I draw a quick graph, we'll have this is the origin. So let's say we started up here. Start. And let's say we finish over here. Our total displacement, if you like, is how far away we are from the origin. So our total displacement is this. Where have we ended up during this journey? So that we could label R, which is the same as the R, this R, and this R, these two guys. These are the same. Total displacement is equal to where we started. So where we started as a vector would be this vector, R0, telling us how to get to the start, plus the vector we moved. So we went from the start to the finish. So you can see that in terms of the vector triangle, going from origin, this is awful, going from the origin here to finish here is the same as going to the start and how you moved. So yeah, you can kind of see this equation forming as a vector as well. Cool. Right, let's move on to constant velocity graphs. So again, these aren't very common, but they all kind of link together. So constant velocity graphs. Whatever. Cool. So we got three graphs. I'm going to do a lot of writing for these ones, I think. So we got displacement, time, velocity time, and acceleration time. I'd like you guys to try this while I do some writing. So we're going to do a displacement time graph, S and T. We're going to do a velocity time graph, V and T, and an acceleration time graph, A and T. So if you guys could try and sketch what you think these will look like. The situation is constant velocity. See what you think we'll get. And I'm just going to type up some definitions so you've got some stuff for your notes. It's a bit of a clue there if you haven't drawn it already. Great spelling there. Let's fix that. Cool. Right, hopefully that was enough time for you guys to try and draw these. Let's just move myself out of the way. Let's go up here. Okay, so for constant velocity, I've said there in text, hopefully you can read that. Velocity is the rate of change displacement. We knew that anyway. E.g., the gradient of a displacement time graph. So if you think rate of change of displacement in the first graph here, 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 where are we? This one here, we're talking about a displacement time graph. So the gradient of this is the rate of change of displacement. So for constant velocity, we're going to have a constant rate of change. We're going to have a constant gradient. So it's going to have a gradient, first of all, and it's going to be constant. So if I draw this, it looks something like that, assuming we don't start at 0. And we can come up with the equation of the line. We know, well, any line has the equation y equals mx plus c. If we think about that on this graph, well, we got s is where y is. What's the gradient? I already said the gradient was velocity, so we could use v. And x, well, we got t. Plus c, yeah, mine doesn't really start at 0, but we can just add on whatever the extra bit is. So we get s equals vt. So these kind of terms all link together. Y is s. gradient is velocity, x is t. Cool. Right, looking at the next one then. Let's move me out the way again. We've got constant velocity. So we're trying to draw a velocity time graph. It means we've got to have a constant line. So there's no gradient, there's no acceleration. I've said constant gradient. That's not really true there, is it? Why have I done that? E.g., no gradient. No acceleration, no gradient. Sorry guys, if you could fix that one. Glad I spotted it. That's going to be just a straight line. Depending whatever your initial velocity was, it's going to stick to that the whole way. So our velocity is the same as our final velocity, v equals u, and we also know a equals 0. Cool, right. For the last one, for constant velocity, there is no acceleration. So we should have acceleration of 0. So just flatline it along the bottom there, and we could say a equals 0. So it's a situation to think about constant velocity. We've looked at the equations now on the last slide. That's the big one. And you kind of see that if r equals r0 plus vt, if we go back to this one, I've used s here, s equals vt plus where we started. Oh wow, what's this? You could equally have done this one with r equals r0 plus vt. If I call it r instead, r equals r0 would be where we started. See it there. And then vt is what we changed, so vt plus r0. Same equation, rearranged slightly differently, and you still get those nice links between your values. And then c where you started. So that's where that equation comes from. Right, moving on. We're going to look at constant acceleration now. So see that. So please only use Suvat equations when you've got constant acceleration, and please only use the last set of equations when you've got constant velocity. So constant acceleration, Suvat is what we kind of call the equations, and is meant to be called kinematics, which is the study of motion with a constant acceleration. Cool. Right, so we're going to start this with some velocity time graphs. We've been looking at time graphs already, so let's have a look at velocity time graphs. So if acceleration, let's type this. This is going to be a bit clearer there. If acceleration is constant, the velocity will increase or decrease at this is so hard to type, a constant rate. So if it's increasing or decreasing at a constant rate, that again means constant gradient, like it did in the last one for when we had constant velocity. So if I draw this, you got v on the y-axis, t on the x-axis. Constant rate means constant gradient. Our initial velocity we call u, and our final velocity we call v. And if we put the time t in there as well, how long we've been moving for, we get this graph. And from this graph, we can derive Suvat equations. So if we look at, there's a couple of ways we could do this. We can try and find the equation of this line. You can think about it in like basic terms, or you can think about it in more A-level kind of terms. If you want to just find the equation of this line, y equals mx plus c is the equation of any line. Instead of y, we've got v. The gradient is a, as we said just now. T is x, and then c is our initial, or where we cross the axis. We cross the axis at u. So you can think about it that way. V equals u plus at is our first Suvat equation. A better way to do it is to do it with the A-level gradient equation. So we know m equals y2 take y1 over x2 take x1. And this is how they'd want you to prove the Suvat equations. So using this gradient equation that we learned at the beginning of the year, we need to look at 2 different points. So y2 is going to be where is it at? Y2 is going to be velocity here, and y1 will be initial velocity. So you can think of these as the 2 points, 1 point here and 1 point here. X values, well, t is going to be our x2, and x1 is going to be 0, which I didn't draw in, but obviously it comes from the origin. So if we fill all of that in, we get the gradient, and the gradient on one of these graphs is acceleration, the rate of change of velocity. A equals y2 take y1, v take u over t takes 0, which is just t. If I rearrange that, we can say v minus u equals at. Add the u over, and we get v equals u plus at. And 3 of those are vectors. So that's our first Suvat equation proved graphically. So you could be asked to do that. They could give you this graph that I'm inside, and yeah, they could ask you to do that proof. So make sure you've got that down. You're happy with it. All right. So there's another Suvat equation we can derive as well. So if we draw that out again, v t t v u. That'll do. Don't mind that. Let's put me down in the. Oh no, what am I doing? Let's put me down in the corner again. There we are. Cool. So from this graph, we can also look at the area. So we've already said gradient equals acceleration. And gradient equals acceleration led us to get v equals u plus at. So that was pretty good. We can also use the fact that the area under a velocity time graph is displacement. And you can think about that in terms of integrals as well, if you like. So the area of this shape, if we have a look at this shape, well, let's draw it all in green. This is a classic trapezium. Area of a trapezium, let's write it down here, equals half a plus b times h. And remember, that's for a trapezium that looks like this, because h is always the height. H can be width as well, though. So if you had A, we had B, h is this length here. We've got a similar thing. You can imagine this is rotated. So it's going to be more like this one. A, B, and H will be... Ha, it's off the page. What am I doing? Let's fix that. A plus BH there. So this is a trapezium we've got. So we can use area's displacement to come up with S, our area displacement, equals half A plus B. Well, A is U. B is our final velocity V. And H is T. So we get half U plus VT. Which generally in Suvat terms, we write the equation as U plus V over 2 T, but you can see that they're actually the same thing. There we go. So that's 2 Suvat equations proved using a graph, which is pretty useful. All right, so what's next? Cool, right, so we're going to basically give you guys all the others. There might be a lot of writing on these ones. So, kinematics equations. So we already proved v equals u plus at, and we proved s equals u plus v over 2t. If you solve those two, oh, I'm writing off the screen again. This is awful. There we go. All right, let me just calibrate this again because yeah, it's not working. Cool. By calibrate, I mean stick some tape to the bottom of the iPad so I know where to stop writing. That should do. Ooh, that should do it. I hope. Yeah, cool. All right. So back to kinematics equations. Cool. All right. So yeah, if we solve those simultaneously, we can eliminate any other variable. We've got two equations there. We could eliminate u, we could eliminate v, we could eliminate t. We can't eliminate a because one of these has already got a eliminated. We couldn't eliminate s in this one because it doesn't have s. So if you solve those simultaneously, you will get the following equations. V squared is u squared plus 2as. So that's eliminating t simultaneously. You could get s equals ut plus half at squared, eliminating v. You could get s equals vt minus half at squared, eliminating v, and that's all five. So 5 equations, 5 variables. Each one of those equations has a variable missing. All right, just to recap what the variables are. S is displacement, u is initial velocity, v is final velocity, a is acceleration, and t is time. Cool. All right, 4 of these are vectors. So S, U, V, and A are all vectors. Because they're vectors, we've got to be really careful about direction. So 4 of these, let's type this as well. 4 of these quantities are vectors. We need to be careful with. If I can type today with their direction. When things are simply moving vertically or horizontally. I say simple because they're only moving in one direction. You know, later on we deal with moving in 2 directions. So simpler ones, one direction. When things are moving vertically or horizontally, we just need to be careful with our signs. Let's say pay attention to when things are moving in 2 dimensions, we need to consider both directions at the same time, or kind of on the same page, one after the other. So when things are moving in 2 directions, projectiles, or occasionally a vector question. So yeah, when things are moving 2 directions, we must consider both on the same page. You could consider both at the same time. If you do them both at the same time, you'd be using vectors. If you do them both side by side, sometimes it's an easy way of doing it. Do horizontal, vertical, and kind of bring them both together when you need to. Together, though, with those equations, you can work out how an object moves with constant acceleration, be it one dimension, 2 dimensions. These would work in 3 dimensions. It's just rare that we have stuff constantly accelerating in 3 dimensions. Normally there's a few more forces at play, forces at angles, but yeah, so that's the basics for kinematics. Right, there's not too much. I know it's a lot talking. I will get you guys doing some questions in a second. So we need to look at constant acceleration graphs because we looked at constant velocity graphs, we looked at velocity time graphs, and now we need to look at all the graphs for constant acceleration. So we've got three. We've got displacement time. We got velocity time and an acceleration time. So if you guys want to try drawing these while I get it all ready, you're welcome to. See if you can race ahead and see what these are going to look like. So S against T, V against T, and A against T. Cool. All right. So displacement time graph. Oh, let's start with an acceleration. We'll start on the right here because I'm here anyway. Start with acceleration time graph. So for constant acceleration, this is just going to be a flat line there at whatever value our acceleration is. So acceleration is constant at a value. Cool. So we can say A equals A. Whatever the A value is, that's A. Caleb, you right there? What's the problem? Oh, no, you guys are just messing around. A equals A, cool. Velocity time graph, well, if we got constant acceleration, it means you've got a constant gradient. So we can write it as that, which we saw already. U, V, T, V equals U plus AT. And V has a constant velocity, has a constant gradient, which is the acceleration. That's annoying, isn't it? I'd like to move that, but I can't. So yeah, I'm stuck with that. And the other one, displacement time graph. Well, this one's harder to think about. I would always think about these in terms of integration. If you integrate a number, so if you integrated a with respect to t, get at, which you can see here. If we integrated a line with a constant gradient, something like this, as you can see, if we integrate something like that, we get quadratic. So we actually need something that looks like a quadratic for our displacement time graph. Something like that's actually pretty good. Something like that. So let's write that on here. Displacement is a quadratic. The gradient of displacement is velocity, and as the velocity increases at a constant rate, the rate of increase of displacement is constant. Okay, that sounds a little bit confusing. So basically the gradient of this ST graph is velocity, and the velocity isn't staying the same. Velocity is gradually, you can see it in this graph here, the velocity is increasing. So the gradient is gradually increasing. We start off with a very shallow gradient, gradient of 0, turning point, and it gets steeper and steeper and steeper, as you can see, as the velocity increases. Yeah, so that kind of links to your calculus. So for this one, to get an equation for this one, it's going to be a quadratic equation. We get S equals ut plus half at squared. And we'll prove that later on. I think not today, but we'll go back and prove this. Cool. All right, let's try some questions. Sorry that was so long-winded and dull, but that's all of constant velocity, constant acceleration, how the equations work, how the graphs look, hopefully a bit more in depth on displacement, velocity, acceleration. We will leave projectiles again for later. That's kind of like an extension of this topic. So I'm going to set you guys some questions. How long have we got? We've got half hour left of our lecture. It's going to be tight. I think I'll just do all of these. So if you guys have to leave at 10:45, um, just leave. But I'll stay here till 11 probably and do a few more examples until my next class begins. So let's try some of these then. So you've got this radio controlled boat. Um, I'm going to give you guys, I think, 3 minutes to do this one. So not 38. Let's change that to 3. So 3 minutes. Can you guys attempt this question? So you got about a minute and a half left. If you guys do it, let's see if see who can find the correct answer first. Comment it in the comments, and you won't win a prize, but we'll make a big deal of it. So yeah, see if you can find the speed and the bearing. Put them in the comment section, and we'll see who gets it first. Should be nice and easy. Got about a minute and a quarter left. Yes, hello. Hey guys, sorry, I was muted there for a bit. Yeah, well done, George. Yeah, 4.61 is correct. Your bearing is not correct though. So let's go through how to do this. So there I am. Cool. All right. So we're talking constant velocity. So we know it's going to be r equals r naught plus vt. And yeah, so let's put everything in that we know. So it starts at position vector 10 minus 5. So 10 minus 5. Passes through position vector minus 2, 9. So that's where we are at 4 seconds. And then we've got vt, so plus v, which is going to be a vector, times t, which is 4. Cool. So if I then take this one from this one, we're going to get minus 12, 14 equals 4v. I can then divide, I'm in the way there, I can then divide those numbers by 4 and get v. So v equals minus 3 and 14 over 4, whatever that might be. So that's my final, or that is my velocity. We want to try and find the speed and the bearing. So the speed will be the size of the velocity. It's the magnitude of the velocity. So speed is going to be square root of minus 3 all squared plus 14 over 4 squared. And if I work that out, it comes to, as, is it George or Caleb? I'm still not sure. 4.61 meters per second. So there we go. Right, we've got to do the bearing though. Remember, bearing is measured from north, which I think might have been what? Clockwise from north. So I think that's where George went wrong. Let's do a quick sketch though. So we've got minus 3, which will be this way. And then we got 14 over 4. 14 over 4 is 3.5. Let's just draw it in now. So there's 14 over 4, 3.5. So our vector is this one. So if we want to measure that from north, north is here. We need to go all the way around until we get to this point. So if we work out this angle, which I'm going to do in blue, this angle here, work out this, let's call it theta. If we work out theta, add on 270 degrees to rotate all the way around until we get to theta. That should do it. So if you want to work out theta, we're going to use tan. So I'm running out of space here, but let's get rid of some prior workings. We don't need all this anymore. Yep. So tan theta is going to be opposite over adjacent, so 3.5 over 3. We don't need to put the minus in because we're trying to find an angle now. We're just using sides of a triangle. I can bring up my calculator. Ta-da! And let's go 1. So we're doing arctan of... Well, I've done that as a vector. I just realized that. Sorry, I'm just used to doing vectors in this question. Opposite over adjacent. Cool. So 3.5 over 3. Let's type that in here. Which gives me 49.4. And then I need to add 270 onto that. So plus 270. So my bearing is, well, my angle is going to be 319.4. That will round down. So my bearing is 319. So there's my bearing. Cool. Oh, I'm in the way. Let's get rid of that again. There you go, bearing of 319 degrees. It was the right digits, George, but all in the wrong order. Cool. All right, let's try another one. So how are we doing for time? 25, 20 minutes. Let's see what we do. Okay, could you guys try this one? And we'll see how you get on. I will give you a few minutes for this one. I'll give you 3 again. Why not? 3 is always a good time. Timer 3. Get started. Again, comment your answers in the chat. Yeah, well done, George. I can those are correct for part A. Well done. You've got 1 second. Oh, close. 350. What's T though? No, haven't quite finished it. Oh, find the position vector. I didn't finish this question. Ooh, okay. Let's go for it. Right. Let's bring me back then. That's bad. I only found the time. Caleb. Oh, cool. I'm so confused at who's who now. Anyway, so trying to find the position vectors at time t. So we're going to be using r equals r naught vt for all of this question. So we got two ships, F and S. Let's do F in red and let's do S in blue. So for F, we're going to say R equals initial position, which was 0, 400. Oh, I see. George is in the classroom and covering everybody. I don't know. So R is 0 plus 400 plus V, which is 77 T. So that's using this bit about F and this bit about F. 400 meters north. Okay, for S, same kind of idea. R equals initial position for this one was 500 meters east. So 500 meters east is like 500 meters in the x direction and nothing in the y direction. So we get 500, 0. Plus VT, well, V is minus 315 times pi T. Alright, so I think, Georgia, these are nice I's and J's. Oh, you're all in the classroom. Well, hey, all of you. Hope you're having a nice day at college. So I'm going to solve these two simultaneously. So when something collides, it's the same place at the same time. So collision collision means occupy same place at same time. So I'm going to solve these simultaneously. So we'll get 0, 400, basically saying that R equals R for this, because the position will be the same. 770 equals 500, 0, plus minus 13, 15, t. So solving these simultaneously, we're going to look at all the x bits first. So x bits, let's do that in yellow. Or I bits if you want to think of it in terms of vectors. So we get 0 plus, let's do it. Oh no, we're going to get, oh, what's going on? Top row, so we're going to get 0 plus 70 equals 500 minus 3t. So that's going to be our first line for x bits. For y, we're going to get 400 plus 70 equals 0 plus 15t. So if we put all those together, we get 70 equals 500 minus 3t. And for the other bits, let's do this in red, y or I bits. We get 400 plus 70 equals 15t. Cool. So if I solve both of these, I don't actually need to do this simultaneously. It's quite simple to do. So we get 10t is 500, therefore t is 50. If I solve this one, I get 8t is 400, therefore t is 50. No, I don't. Something like that. Have I done something wrong here? What have I done? Yeah, that's fine. 8t is 400. What am I talking about? So therefore t is again 50. Okay, so if I want to find out where these things are when they collide, I just need to put 50 back into either equation. So let's choose an easy one. They both look about the same, so we'll go with f. So f over here, we're going to use that. We're going to put 50 in as t, so r equals 0 plus 7 lots of 50. And on the bottom, it's going to be 400 plus 7 lots of 50. So r equals, was George right with this? 350i, I agree with that. And for J, yeah, we got 350 plus 400, which is 750. Well done, George. Good job. Or Caleb. Well done, Caleb. Sorry. Whoever it is, well done. Well done, people in the classroom. Can I do the air horn again? Right, let's move on. So, how long have we got left? We got 10 minutes. This is going to be tight, but let's see what you guys can do. Let's make it harder. Let's make 2 minutes for this one. See what you guys can do in 2 minutes. I'm expecting a lot of my verbal maths class. Go, go, go. Good luck. Cool. All right.
Cool. Right, let's let's try this one. I noticed nobody got any answers yet, so if you guys want to keep working at it. Oh wait, we're in. Roddy says 2.5 seconds, 2.5 seconds, half of 5 seconds, quarter of 10 seconds, 5 over 2 seconds, 5 times 0.5 seconds. Well done, Roddy. Let's do it. Can you guys hear me? Air horn should be there. I don't know. Maybe it's not working today. We'll see. Anyway, well done there. Cool. Right. So let's race through this one. I actually planned to do like another 10 questions, so it shows how fast I thought we get through stuff. So I think Monday's lecture, we'll finish off this topic just smashing through examples, and then we'll consider this topic completely revised. Cool. All right. So we've got our mouse. We're going to be using r equals r0 plus vt again. So let's set it up. R equals r0 plus vt. So we got 6 minus 3 is where we're trying to end up, where our mouse is headed. It starts minus 2, 3. I think it's a shame it's a clockwork mouse. A live mouse would be much more interesting. Constant speed of 4. Ooh, interesting. So we got vt. We need to write vt because v is not speed. Let's put that in red. V is a vector. So 4 is not v. Cool. All right, we're going to do this as vectors. So I'm going to call my velocity vx, vy. So we got 6 minus 3 equals minus 2, 3 plus vx, vy times t. And I know that velocity vx, vy, the magnitude of that is our speed. So vx squared plus vy squared is actually 4 squared. So we can kind of draw that as well. So we know the speed to be 4. I don't know if I've drawn an angle. I guess angle works. We've got vx and we've got vy. So in other words, 4 squared equals vx squared plus vy squared. So in other words, 16 equals vx squared plus vy squared. Cool. Alright, so we're going to try and solve all the x, y, and z bits separately. I can add my vector here, 2 minus 3, onto this side to just get something equals vx, vyt, and then we can solve simultaneously to try and find t. How are we doing for time? 5 minutes, yeah, I'll be fine. Alright, so if I rearrange the blue equation, we're going to get 8 equals vxt, and we're going to get minus 6 equals vyt. I could put all these together. So I'm going to basically rearrange these to get vx and vy. So over here, vx and vy. I'm going to put those into this equation and solve it to try and find what t is. So these will lead to vx equals 8 over t. This one will lead to vy is minus 6 over t. And I'm going to put those into this equation above my head. So we'll say 16 equals 8 over t squared plus minus 6 over t squared. Rod, is this the same method that you used, or did you try anything else? Curious to see how you did it. So if we expand all that, we can say that 64 over t squared plus 36 over t squared equals 16. 16. I can times both sides by t squared. To get 100 equals 16 t squared. And if I solve that, we get to t equals 2.5. Cool. So well done for solving that. If you've got any questions about this, please comment it. We've got 4 minutes left. Should we try one more? I'm assuming you guys are going to say yes, because I know there's a 5-second lag. I'm going to assume you all said yes, Alex. Let's do one more question. So we got this car moving along a straight road. This will be easy. Yeah, we've got time to do this. So we're looking at velocity time graphs. The next few questions will be on velocity time graphs. We'll do one today, and then the rest will finish off next week on Monday. So if you guys could try this, I will set a 2-minute timer this time. Again. If you guys could give that a go. Let's do it. Oh, George, you said no. You should have said no faster than that. So it's too late now. The time has begun. Can I pose for a photo after this question? I suppose so. Got to keep my viewers' interest up. So yeah, I'll do a quick pose. How are you guys stuck already? Draw a velocity time graph. Easy. Find the distance. Distance is the area. Find the area of the trapezium. I'll give you a hint. I'll start drawing the graph for you. So part A. It's been a long day. Lecture 1 and it's been a long day. We have done quite a lot today, I guess. So we've got 10 there. Across we go. Down we go. 30. 42. There's your velocity time graph. Well done. Part B, distance equals area. Oh, it's time up. So, anybody got it? Area, remember, half A plus B H. Nope. Alright, so we got half of 42 plus 30. So that's our, what am I talking about now? A plus BH. Yeah, so we got A is going to be this bit here. Let's do it in yellow. A, B, H. What am I doing for this pose then? After, cool. Yeah, let's finish this off. So, half A plus BH. A is 30, so half 30 plus 42 times 10. And that should give you 360 meters. Cool. Right. I hope that was all good today, guys. So this will be how we teach from now on. Monday's lesson will be at the normal time. I know college have said they're not doing video learning till Wednesday, but I thought, why not? Let's plow ahead, get through content. Okay, let's do that. Here we go. Hey guys, you gotta send me this photo later. I don't know what's gonna be. Yeah. So next week, yeah, Monday and Tuesday's lectures will be as per usual, but on here. Email me if you've got any questions between now and then, and we'll work out a way to do some homework questions via Microsoft Teams. I think we'll work out something so that we can get some homework done as well, but it will be mainly revision. Cool. All right, cheers guys. I will see you on Monday. Well, you'll see me on Monday. You guys are posing. We'll be doing a group photo. All right, we'll do this quickly, then call it a day. Here you go. Cool. All right. Cheers, everyone. Thank you. See you next week. Email me if you need any help or comment. Thank you. Bye.